All right, welcome back. Here are just a couple of reminders from our quadratics unit. First, always start with a GCF. Second, if it's a binomial, check to see if it's a difference of two squares. Third, if it's a trinomial, start by using the factor x. If a is greater than 1, then continue factoring by grouping or by the slip and divide. If the polynomial has an even number of terms, in other words 4 like we've been doing in class, then use the grouping. So these are the same ones we did in class. Even if you've done them already and you're coming back and watching the video, it's still beneficial to get the practice of going through the steps. So I still encourage you to come through and give them a shot again. So go ahead and practice all 5 and then come back and check. Welcome back. We're looking at factoring. Well, I see that I have a binomial and both of these are perfect squares. So I can take the square root of both. The square root of t to the 4th would be t squared. The square root of 16 is 4. So we're going to end up with t squared plus 4 and t squared minus 4 as our factors. Now, let's make sure that we're paying attention because look, we have another subtraction sign. And if I have another subtraction sign, I probably want to check for a difference of squares. T is squared, that's a perfect square, and 4 is a perfect square. So once again, we're going to have to break this down. The square root of t squared is t. The square root of 4 is 2. T minus 2. Now our other binomial that we had has an addition sign, which means it's not a difference. So we don't have to worry about difference of two squares. We simply bring it down. And those are our factors. Number 2, 3x squared plus 12x squared minus 2x minus 8. This is an excellent example of grouping. So we would want to group. Notice I captured that subtraction sign because I'm treating it like the additive inverse. So I'm going to add negative 2x. Now we simply want to find our GCF. GCF and 3x cubed plus 12x squared. Well, that would be 3x squared, which is going to leave us with x plus 4. Now, when we set up our second parentheses, we really want the first term to be the same. So what can I divide negative 2x by to get x? That's right, negative 2. If I divide negative 2x by negative 2, I need to divide negative 8 by negative 2, so that gives me plus 4. That's what we're looking to see. That means x plus 4 is one of our factors. And then we take the remaining values and put them together to make our other factor. Number 3, 2x to the 4th plus 8x cubed plus 6x squared. Well, here it looks like we need to find a GCF because I've got a lot of even numbers and a lot of powers. So let's start with 2 goes into all 3 numeric values, and it looks like x squared goes into all 3 variables. 2x squared into x to the 4th is going to leave me with x squared. 2x squared into 8x to the 3rd is going to leave me with plus 4x. 2x squared into 6x, well, that 2 goes into 6 3 times. And we've factored. Well, next we want to check our trinomial to see if it is factorable. So I'm going to do our x games. Plug our 3 in the bottom, our 4 in the top, and see, do we have two numbers that multiply together to give us 3, that add together to give us 4? Well, 3 times 1 is 3, 3 plus 1 is 4. So these are our factors. X plus 3, x plus 1. Now at this point I want to go ahead and remind you, factors are not solutions. Solutions are values for x. All right. Now the last thing I want to do, we pulled out this GCF. Let's bring that over too because that's also one of our factors. So we end up with 2x squared times x plus 3 times x plus 1. Number 4. We have a leading coefficient of 1, so we can go ahead and try our factor x. We need two numbers that multiply together to give us 2, add together to give us 5. Well, our factors of 2 are 2 and 1, and no combination of 2 and 1 is going to add up to 5. So this trinomial is already prime. Again, while it may be factored as simple as it can get because it is prime, it still has solutions. All right, number 5. Number 5 has a leading term that's greater than 1, so we're going to have to use our x games, but we'll need the slip and slide version of it. So 8 times negative 5 is negative 40. And we want them to add to negative 18. So two numbers that multiply to negative 40 looks like probably going to be a 20 and a 2. And we need a negative version of the 20 so that we get to negative 18, and a positive version of the 2 so that we come back up the number line to 18. So we're replacing negative 18x with negative 20 plus 2. So we'll have 8x squared minus 20x plus 2x minus 5. And we want to group. All right, so 8 and 20 are both divisible by 4. 4 goes into 8 2 times. Four goes into 25 times. 2x and 5 are both divisible by 1, which leaves 2x minus 5. We can see that our parentheses values are the same. So we put together the numbers outside the parentheses, 4x plus 1. We put together or keep one of the values inside the parentheses because that was also a solution. And we have found our factors to be 4x plus 1 and 2x minus 5. Now today we've solved exponential equations. And for solving exponential equations, we really relied on a number of our exponent rules. And I know it's been a while since we've seen the exponent rules, which is why we started out the spring semester with a review of exponent rules on Wednesday. And so if you have not gone back and reviewed your exponent rules in preparation for turning that in next week, I highly recommend that you go ahead and do so. Steps to solving the exponential equations. Two powers with the same positive base b, where b is not equal to 1, are equal if and only if their exponents are equal. So if 5 to the x power is equal to 5 to the 8th power, then x would be equal to 8. Since the bases are equal, we can set the powers equal to each other to identify the value of the missing variable. Now, this is going to be heard over and over and over and over as we progress through the unit. Since the bases are equal. Now, it is very important that your bases are equal when we're setting our powers equal to each other. If their bases are not equal, you can't set your powers equal to one another. So, for example, 5 to the x is equal to 5 to the 1/2. In both instances, our base is 5. So we can set our powers equal to one another. X is equal to 1/2. Well, the question asks for us to solve, and every time we've solved before, whether it's a quadratic or a linear equation, we solve by finding the value of x. Notice, we've already done that. So the value that satisfies x in this equation is 1/2. All right, again, we have a value of our base is 3. Those are both the same, which means we can set our powers equal to each other. 3x plus 6 will be equal to 5x. Well, at this point, we have a two-step equation. So we'll subtract 3x from both sides. 6 is equal to 2x, and we'll divide by 2. X is now equal to 3. Now, you can certainly check your answer if you'd wish. You could say 3 times 3 is 9, plus 6 is 15, so we end up with 3 to the 15th power. And we plug in x on this side. 3 times 5 is 15, 3 to the 15th power. And it shows, sure enough, 3 to the 15th power is going to be the same thing as 3 to the 15th power. 4 to the x power is equal to 1/4. Now, this one's going to take a little bit of manipulation now, because we can see I have a base of 4 and I have a base of 1/4. But remember that 1/4 is also 1 to the first power over 4 to the first power. And there's no reason why we can't have a negative power at this point if it benefits us in having an identical base. So we can take the power and its base, move it across the fraction bar, and 1 over 4 with a power of 1 when it comes upstairs becomes 4 to the negative first power. So we're essentially saying 4 to the x power is equal to 4 to the negative first power, where we can clearly see that our bases are the same, so we can set our powers equal to each other. X is equal to -1. We've found the value of x. 7 raised to the x minus 2 is equal to 7 raised to the 0th power. Now, by now, you should be starting to get into a little bit of rhythm. If you want to pause the video and give it a shot before I walk you through the answer, that's probably a good idea. 7 to the x minus 2 is equal to 7 to the 0th power. Both have bases of 7, so we can set the powers equal to each other. X minus 2 is equal to 0. Add 2 to both sides, and x is going to equal 2. Well, that makes sense. If I plug a 2 in for x, 2 minus 2 is 0, so both sides of the equation would read 7 to the 0th is equal to 7 to the 0th. Number 5, 2 to the x minus 2 is equal to 1. Well, that's an interesting problem, because base of 2 and base of 1, these are not the same thing. But we should remember from one of our exponent laws that there is a particular exponent law that always results in a solution of 1. And that particular exponent law is any value raised to the 0th power. That kind of helps us out a little bit here, because we're looking for a base of 2. So could I not also say 2, which is any value, raised to the 0th power is equal to 1? Yes, we can. And so now at this point, I can plug in place of 1, 2 to the 0th power, which is going to be equal to 2 to the x minus 2 power. And so now I have like bases. We can set the powers equal to each other. X minus 2 is equal to 0. Add 2 to both sides, and x is equal to 2. Yes, this was an identical problem to the previous one. All I really did was change the 7s for 2s. But it started introducing that understanding of our exponent laws can be used to help us manipulate numbers. And as we manipulate numbers, we can create bases that are identical. And so this is going to be an important part of us working through this unit, is being able to create bases that are identical. Solve 5 to the x plus 1 times 5 to the 4th is equal to 5 to the 12th. Now, before I really do anything, if at all possible, you always want to simplify one side of the equation. That's kind of been a norm since 6th grade. Well, here we see that we have like bases, and when you have like bases, you can add the powers. So 5 to the x plus 1 plus 4. Well, when we have 5 to the x plus 1 plus 4, we could certainly say 5 to the 1 plus 4 plus x. That's our associative property of addition. That basically says it doesn't matter what order we add these values in. We're still going to get the same solution. If I kick something out of the parentheses, I can bring another value into the parentheses and still retain the integrity of the equation. So now we can simplify. 1 plus 4 is 5, which gives us 5 to the 5 plus x. And remember, so far all we've done is simplify what's on the left side of the equal sign inside the box. So let's bring down the rest of the equation. Equals 5 to the 12th power. Well, now we can clearly see that we have like bases, so we can set our powers equal to each other. 5 plus x is equal to 12. Subtract 5 from both sides, and x is equal to 7. Number 7. Well, this is a little bit different because we don't have bases that are equal to each other. I've got a base of 3 and a base of 27. Hopefully right now, though, your brain is thinking, hey, I know 27. We studied that last year. That was one of our perfect cubes. 1 cubed is equal to 1. 2 cubed is equal to 8. 3 cubed is equal to 27. 4 cubed is equal to 64. 5 cubed, is equal to 125. These were ones we memorized last year for the purposes of getting ready for our understanding of math concepts this year. It was intended for these to be ingrained in your brain so that as we started working through these types of problems, both in factoring and in solving exponential equations, your brain was already trained to identify number patterns. So 27 is the same as 3 to the third power. So 3 to the third power raised to the x power is equal to 3 to the x minus 4. Well, now I can see I've got a 3 at least for a numeric value, but we still got to do something over here. So thinking back to our exponent laws, we have a power to power law. It basically tells us when I have a power raised to a higher power, we multiply the two powers together. So that will give us 3 to the 3 times x, which is 3x, which equals 3 to the x minus 4. Now we're finally at the position where our bases are the same. So we can set our powers equal to each other. 3x equals x minus 4. And with a little bit of two-step equation, we're good to go. We subtract x from both sides. 2x is equal to negative 4. Divide by 2. And x is equal to negative 2. Seven is equal to 7 raised to the 2x minus 4. Now, one of the things I'm going to highly encourage you to do is anytime you have a base with no exponent showing, go ahead and write it in so you know what it is. Because the natural tendency when you set up an equation like this is going to be to say that that value is 0 because there's nothing there. Please don't be one of the few students that makes that mistake. The exponential power for any integer is 1. So since our bases are the same, we can set our powers equal to each other. 1 is equal to 2x minus 4. We'll add 4 to both sides. And 5 is equal to 2x. And we finally divide by 2 and learn that x is equal to 5 over 2. Go ahead and leave it as a fraction. No point in wasting time changing it. Now here's 3 that I want you to definitely try. So pause the video, then come back and see how they're worked out. All right, welcome back. Well, we have like bases, so we can set the powers equal to each other. 5x is equal to 2x plus 3. Subtract 2x from both sides. And 3x is equal to 3, so x must be equal to 1. That was a pretty standard, straightforward problem. B, on the other hand, is a little bit different. One of the things we should remember about square root is the square root, or radical, written in exponential form, is 7 to the 1/2 power. Oops. Now, since we have 7 to the 1/2 power, we now notice that I've got two bases that are identical, so I can set the powers equal to each other. So 1/2 is equal to x plus 4, where I'm simply going to subtract 4 from both sides And we get negative 3.5, which is negative 7 over 2. Now, this is not the only way to solve this particular problem. You can also recognize, hey, that's a square root, a radical. I can square it. Well, the square root of 7 squared is square root of 7 times square root of 7, which is the square root of 7 times 7, which, lo and behold, is simply just 7. Is equal to 7 to the x plus 4, and what we do to one side, we have to do to the other side, we square it. And at this point, we should be thinking, hey, I have a power raised to a higher power. So we want to multiply those two powers. 2 times x plus 4. 2 times x is equal to 2x. 2 times 4 is equal to 8. And so we have 7 now raised to the 2x plus 8 power. Remember, anytime I have an integer, I want to go ahead and identify its power so I don't make mistakes. But we have like bases, and we can set the powers equal to each other. 1 is equal to 2x plus 8. So we'll subtract 8 from both sides. Negative 7 is equal to 2x, and we'll divide by 2. X will be equal to negative 7 over 2. Either way, you end up with the same solution. All right, 7 to the 3x is equal to 2,401. And so on this particular problem, either 2,401 is going to be divisible by 7 an even number of times, or we're not going to have like bases. It's as simple as that. So let's go ahead and take our 2,401 and divide it by 7. Well, that comes out evenly, so it's looking pretty positive. 2,401 divided by 7 is equal to 343. Well, let's see if we can divide that one by 7. We can, and that gives us 49. Well, 49 we know is divisible by 7. That equals 7. And 7 we know is equal to 7. That gives us finally 1. So we can see that I have to multiply 7 4 times to equal 2,401. So that's the same as saying 7 to the 4th power, which is equal to 7 to the 3x power. So again, we have like bases. We will set the powers equal to each other. 3x is equal to 4, where we'll divide by 3. And x is equal to 4/3.